All right, we're approaching the end of chapter 5 and likely the end of the course. Section 5.8 really just rehashes something we did back in chapter 3, and the topic is singular value factorization. General declares the singular value decomposition useful in solving linear systems. Why do factorization? To simplify computations is likely why you do it. We'll just recall the definition of singular value decomposition with a little warning here. When we use the word factorization, that's synonymous with decomposition. Those are interchangeable. Back in chapter 3, it was section 3.8, we defined for n by m matrix A, factorization A equals UD V transpose, where U is an n by n orthogonal matrix, V is an m by m orthogonal matrix, and D is an n by m diagonal matrix with non-negative entries, is a singular value decomposition of matrix A. Little comment, maybe this collides with your experience in sophomore linear algebra, but when we say a matrix is diagonal, it doesn't have to be square. We define the diagonal of matrix D to be the entries D sub I, as I ranges from 1 to the smaller of these two. So we do have a meaning on, there's the smaller of the two, we do have meaning to the idea of a diagonal matrix, even though matrix might not be square. These non-zero entries in that matrix D were called the singular values of A. And we showed in section 3.8 that every matrix there exists a singular value decomposition. All matrices have singular value decompositions. Gentle makes a comment that singular value decompositions are rank revealing, since the rank of A is the number of non-zero singular values as given by the diagonal of D. Okay, I can determine the rank of A certainly by looking at the rank of D. We wrote A in terms of UD V transpose, UD V inverse if you like. V is an orthogonal matrix, so the transpose and the inverse are the same. These U and V matrices, they're square. They're orthogonal matrices. They're invertible. All orthogonal matrices are invertible. All square orthogonal matrices are invertible, I should say. And their inverse equals their transpose. So the U matrix and the V matrix are themselves products of elementary matrices since they're invertible. And it's theorem 3.3.3 that will tell you then the rank of A equals the rank of this little matrix here. We've multiplied by products of elementary matrices. P and Q were the symbols we usually used for those. But in that sense, I would agree, we've got rank revealing. And it's easy to find the rank of a diagonal matrix. You just go through and count the number of non-zero diagonal entries. And that takes care of this very short section. So we've got, I think, 2 more sections left in chapter 5. And that'll likely wrap up the course. Have a nice day.